Okay, this is the first of the examples I'm going to go over. So today's lesson is going to be on complex roots, and I'm really just consolidating what we did last lesson. So there's no new learning as such, but it's just bringing in a few things that we've talked about. So we have, to start with, verify that z equals 1 plus 2i is a root of this cubic. So to verify that 1 plus 2i is a root, I need to plug in 1 plus 2i for z and show that you get a 0. So I'm looking at doing 4 lots of 1 plus 2i cubed minus 11, 1 plus 2i squared, plus 26 lots of 1 plus 2i minus 15. And you know you're looking to get 0, but we need to show it's 0. I would do a binomial expansion there. So 1 plus 2i cubed. You don't have to do the table. I quite like the table. So 1, 3, 3, 1, 1 cubed, 1 squared, 1 to the power 1, 1 to the power 0. 2i to the 0, 2i to the 1. 2i times 2i is 4i squared, which is minus 4, times another 2i minus 8i. So that binomial expansion multiplying across is 1 plus 6i minus 12 minus 8i. And then I need to subtract 11 lots of 1 plus, expanding this, 4i, 2i squared is minus 4. And then 26 minus 15 is 11. And then 26 times 2 is plus 52i. So tidying up again. It's just getting that balance as to how much you want to write as well. So 1 minus 12 minus 11 times 4 is negative 44. 6i minus 8i minus 2i times 4 is minus 8i. 1 minus 4 minus 3 times negative 11 plus 33 minus 44i. And you'll know if you've gone wrong because you won't get a 0 when you add them all up. And then you can find where you went wrong. That's always the fun bit. So let's have a look. Minus 44 plus 33 plus 11 is 0. And minus 8 minus 44 plus 52 is 0. So equals 0 as required. And then from there we can look at finding the other roots. And in an exam you'll be told to use an algebraic method. So you can't just whack that into your calculator and write them down. That's cheating. So z equals 1 plus 2i is a root. And we know that complex roots come in complex conjugate pairs. So z equals 1 take 2i is a root. And a cubic will have 3 complex roots. So if it's 2 complex, it will have 1 real root if you think about it. Let alpha be the third root. And then we can go into the work we've been doing on sums of roots and sums of the product of the pairs, sums of the product of the triples, etc. So I think the easiest thing to do would be to add these together. So the sum of all the roots is equal to, and then the sum of the roots is minus, so we've got this alternating sign, so it's negative 11 over 4, which gives you 11 over 4, or minus negative 11 over 4, probably should have said. So sum of the roots equals 11 over 4, and so adding them together, again these brackets aren't necessary, but it just shows nice and clearly what's happening. Imaginary parts cancel off. And then subtracting 2 alpha is equal to 3/4. So that's all 3 roots. So to start with, if you could look at exercise 3.4, page 63, questions 2, 5, 6 and 12 is just like a little true or false one. Don't feel like you need to finish all of them, see how you get on, but do maybe kind of a good half of the lesson sort of time on this, and then I've got a couple more examples and a few more questions, so work at your own pace. If you could all help each other as well, if you get stuck, please ask someone else and work together. And yeah, I'll record another video for the next one. Okay, bye.